Exercise 50. Let's talk about this real symmetric matrix. The spectral theorem. For symmetric matrices. And by n symmetric matrix A have the following properties. Firstly, it has real integer values. Counting multiplicity. Secondly, the dimension of each engine space equals the algebraic multiplicity of the engine value. Where the algebraic multiplicity of lambda is the multiplicity as a root of its characteristic polynomial. Thirdly, the engine spaces are mutually orthogonal in the sense that any different engine values, their corresponding engine vectors are orthogonal. So in general, recall that for a matrix not necessarily symmetric, different engine values corresponding to engine vectors linearly independent, but here it's stronger. We require them to be orthogonal, or they happen to be orthogonal. I mean, E1 is denoted by the engine space of lambda 1, E2 corresponding engine space of lambda 2. If lambda 1 doesn't equal lambda 2, then two engine vectors V1, V2 will be orthogonal. Lastly, it orthogonally diagonalizable. So this is already proved. This exercise 49. So let's see the proof. Let's first see this C. So notice that you have wave 1, wave 2. So the dot product could be computed by matrix multiplication. So when there is no confusion, let's remove this arrow. We know this is talking about the vector. So the transpose commutes with scalar multiple. And here comes the fact A is symmetry. Should be with AT, but because A is symmetric, this is also close to this. And then we say this is and so lambda 1 doesn't equal to lambda 2 implies the orthogonal. So here obviously we're using the dot product. That's why for dot product we have this general X transpose Y corresponds to X dot product with Y, right? Remark. So you could replace a dot product with other inner products, but as we have discussed before in previous exercise, maybe exercise 44, 45 maybe, there you would, if you're not talking about dot product, you're talking about some matrix multiplication. Instead of taking A equals identity, is any or some symmetric positive definite matrix. That's the remark. Okay, so we prove C. So let's continue. How about A? So actually recall that we have n complex eigenvalues counting multiplicity. This is because the characteristic polynomials always have n solutions. Counting multiplicity have n complex solutions, right? And then if you have n complex eigenvalues plus the fact A is symmetric, so let's say you have a acting on V equals lambda V. Lambda is complex number, but if A equals A transpose, what can you say? Question. Sub-exercise. Show that lambda is hence a real number. So let me write down this sub-exercise. Take n by n real matrix such that it is symmetric. Show that A x equals lambda x for some non-zero vector with complex in G, then lambda is real and the real part of x is eigen vector of A. So this is what we want, right? So real matrix. Actually, this is what we are talking about here. We are talking about real matrix. We're talking about real symmetric matrix. So let's first give hint for this sub-exercise. Compute conjugate of x transpose the ax. Let me add also sub-exercise. Under the same assumption, so we have matrix A, which is n by n real matrix. That is symmetric. And x p-adic again, complex in sheet and by one column vectors. Still Q the transpose of x, then ax. The quantities below. Show that Q is actually a real number by verifying conjugate of Q equals Q. Q bar equals conjugate of x bar tax, and this further equals so the conjugate transpose and then take the conjugate is the same as the transpose. Is symmetric, is real, so this is X transpose AX bar. Notice this is also the transpose of this. The reason that this is a 1 by 1, which means this is a complex number. So together, which means this is a complex number, and so it equals this transpose. So if you apply this transpose here, this is the transpose A transpose, which is again A and X. And this goes back to Q. And so we have proved this is always a real number. Now let's come back to this sub-exercise. With this fact here, what can we say about this? This equals X bar transpose, but X is in G vector, and so this equals lambda X bar transpose X. Alright. So what is this? This is, so suppose your X is X1, X2, Xn. This is X1 bar, X2 bar, Xn bar, and then X1, X2, Xn. Obviously, I mean this is a real number. And so this is a real number by this sub-exercise. And this implies that this must be a real number. What did we use? We used the fact it is real and symmetric to prove this. And then we use this observation. This is just lambda times a real number. So lambda is a real number if and only if this is a real number. And so this is the case by this exercise to tell you that it is a real number. So we're talking about this real matrix. The left one is to show the engine space. But this follows from the orthogonally diagonalization. Basically, let's see what happened. Recall that in general, general for n by n matrix, real matrix. Without the assumption it is symmetric, what do we know? We know that if you have eigenvalues with corresponding multiplicity d1, d2, let's see, dm, then the dimension of lambda, an eigenspace corresponding to lambda, so dimension of E1 will be less equal than D1, correspondingly dimension of En less equal than Dm, and A is diagonalizable if and only if this dimension of E1 plus dimension of Em equals n, right? And so here, by this factor that A is symmetric, imply this D, which is orthogonally diagonalizable, in particular is diagonalizable. So this D implies this is the case, right? It is diagonalizable. This is by what is stated there. And then this implies, in particular, this is the case. This is in particular telling you that the dimension of E1 equals D1, dimension of Em equals Dn, which means the eigenspace of each eigenvector corresponds equals its algebraic multiplicity, because it's D1 plus Dm equals n. Because your characteristic polynomial could be written as in general, of course, it could happen that it does not have real solutions, but it always have complex solutions. But in particular, as we said, when it is symmetric, we have proved in small a that these are all real. These complex eigenvalues or the complex roots are actually all real roots, and so this multiplicity add together to be n, and so the summation of this will be less equal than the summation of this, but this equals n, and we know this equals n, which means each term is an equality.